We are further continuing with the fluid mechanics or the mechanical properties of the liquids. Now, our discussion is regarding the Pascal's law, then its applications, and after that we will discuss about the laws of flotation, the buoyancy, and the Archimedes principle. Pascal's law states that liquid transmits pressure equally in all directions. This is what is the statement of Pascal's law. If we consider a rubber ball and from one end it is slightly cut from the top and some liquid is filled, and then if we make some holes in it and we press the ball, we find liquid transmit pressure equally in all directions. That is, we will apply pressure, the liquid will come out in all the directions and the pressure will be same. So this is what we have to apply in the various devices. Earlier, we have seen that the pressure difference between the 2 points depends upon their horizontal and vertical separations and acceleration of the container. Suppose by some means the pressure at one point of the liquid is altered without altering any other parameter mentioned above. The pressure at all other points must also change by the same amount so that the pressure difference must remain the same for given 2 points. This is what I have suggested earlier, that is, liquid transmits pressure equally in all directions. The Pascal's law, we can put it in many ways. Like I have explained it, that liquid transmits pressure equally in all directions. Here the concept is, if the pressure in a liquid is changed at a particular point, the change is transmitted to the entire liquid without being diminished in magnitude. It can be, in a very simple form, can be said that liquid transmits pressure equally in all directions. Now we come towards the application of the Pascal's law in hydraulic lift or a jack. Normally, in case of hydraulic lift, we have to pick up a very heavy load on a particular platform, and this is carried out according to the principle, that is the Pascal's principle. For a hydraulic lift, we find there is a lot of liquid in particular portion, and when a load is kept on the platform, then we find that pressure is working upward, and like the car or heavy load will be moving upward, and if it is a car, we have to check up its suspension, and that's why the car must be lifted. The pressure due to small force F1 applied to the piston of area A1 is transmitted to the larger piston of area A2. The pressure at two pistons is the same because they are at the same level. So, pressure is given by force by area, that is, pressure will operate equally on both the points, that is, piston with area A1 and A2. Forces will be F1 and F2. So, pressure at the two pistons will be F1 over A1 and F2 over A2, and they will be numerically equal. So, we can calculate the force at the another piston, that is A2 by A1 multiplied by F1. Generally, A2 is much greater than A1. So, force F2 must be much greater than F1. Now, in the adjoining figure, hydraulic lift is indicated. On the right hand side, the piston is A2, or there is a piston on the right side and there is a piston on the left side. We will apply small force on the left piston with area A1, and that small force is sufficient to carry the car or the load upwards. That is where the area is A2 and the piston is having more area, and we find the force will be more. So this is the right side where the hydraulic lift is indicated, carrying a heavy load. There is no gain in terms of work. The work done is same for both F1 and F2. The piston A1 has to traverse a larger downward distance as compared to the height raised by A2. Now we come towards atmospheric pressure. Regarding atmospheric pressure, it means we are referring to atmosphere, that is air. How much pressure air will exert at the various points in the atmosphere. First of all, you can remember that pressure is force per unit area. Number one. Number two is force is pressure multiplied by area, and the unit of pressure is Newton per meter square, or it will be Pascal. 1 Pascal and 1 Newton per meter square is same thing, and bar is the biggest unit. Now, atmospheric pressure, as we moving to the higher points, that is on the cliff of the mountain, we find the pressure is very low. That is, atmospheric pressure is low. But as we start moving downward, so near the ground, the pressure of air will be more, because there is a lot of volume of air working on us. Like, for example, our body contains blood, and if an astronaut will be sent in the space without the astronaut suit, we will find the blood will ooze out from the astronaut because there is no atmospheric pressure. So liquid will have the pressure in one direction, and finally the body will go on expanding, and at a particular point it will burst like a balloon. So now we will come towards the main concepts of the atmospheric pressure. At the higher point the pressure is low, and at the lower points we will find that the pressure of atmosphere will be more. The air above the Earth's surface presses the body on the Earth. It is known as atmospheric pressure. Atmospheric pressure at the top of the atmosphere is zero. So it's not exactly zero, but it is approaching zero, as there is nothing above it to exert any force. Thus the pressure at distance h below the top will be pH, and that is integrating the function rho g dz from limit 0 to h. Now rho g will be taken out the sign of integration, and we will integrate 1 dz, which is found to be z, and for z we will compute the value 0 to h. So it will become h minus 0, and the function will become rho gh. Now neither rho nor g can be treated as constant over the larger variations in the height, because the composition of air will change possibly. Value of atmosphere, that is given as 1 atmosphere or atmospheric pressure, is 1.013 into 10 to the power 5 Pascal. Now we come towards what is basically an absolute pressure, that is P naught, and the gauge pressure. So in order to set up the relation, it's like that the absolute pressure at point A is the total pressure at that point, including the pressure of liquid and that of the atmosphere. So if a point is within the liquid, that point is experiencing pressure due to liquid as well as atmosphere. Gauge pressure is relative pressure between the 2 points, of which one is at the surface and other is at some distance below inside the liquid. Now absolute pressure will be given by the algebraic sum of gauge pressure plus atmospheric pressure. Here in the given situation, gauge pressure will be equal to rho gh, because absolute pressure, therefore absolute pressure can be written as P naught plus rho gh. P naught is absolute pressure, rho gh is gauge pressure. Absolute pressure is always positive, whereas the gauge pressure can be negative as well as positive. Now we will further extend our idea of the absolute pressure and gauge pressure. Absolute pressure at point A. We can see the figure. Point A is within the liquid. Atmospheric pressure is acting P naught and the liquid pressure will be H rho G. So, absolute pressure, now we come towards the main concept. Absolute pressure at A is total pressure at that point, including the pressure of the liquid and that of the atmosphere. The second is gauge pressure is relative pressure between 2 points of which one is at the surface and other is at some distance below inside the liquid. Therefore, absolute pressure will be gauge pressure plus atmospheric pressure and we can write it mathematically rho GH or it is P naught plus rho GH and absolute pressure is always positive whereas the gauge pressure can be negative as well as positive.